Okay, so the test is on next Thursday. I could actually do it Tuesday, but it's actually for my benefit, so I can get everything ready on Tuesday of next week. So the other class is taking the test Wednesday, but they're actually a day behind you guys, so anyway, it doesn't really matter. So I will put a review video up before the weekend, and I'll post it on the YouTube channel under reviews. I may have already done that, but anyway, if I haven't done it, I'll do it today or tomorrow. So remember, you can bring in a sheet of paper with whatever you want to put on there. You can use your calculator, but for the calculations that involve factorials like permutations and combinations, I want you to write out the formula. Put in the numbers in the formula and show how you would do it if you don't have a factorial thing on your calculator, just so everybody's on the same playing field. I'm not going to come by and see if you use your factorial thing on your calculator, but you're still going to have to do the calculations the other way. You check, I guess you could verify that you did it correctly if you do have factorial on your calculator, but I do want to see the intermediate results. So if I put something up like you know, calculate or just evaluate you know, 15 things taken 3 at a time as a permutation, I don't want to see just an answer. You'd need to put 15 factorial divided by 15 minus 3 quantity factorial. You'd need to then do the math in the parentheses, and then you would rewrite the numerator as 15 times 14 times 13 times 12 factorial divided by 12 factorial, and then you can cancel those out, and then you can give me the number. Okay, so that's what I'm expecting. If you give me a number, just a number, I'm not going to give you any credit. 0 credit. Yes, Dana. Which section is that? Oh, okay, sure. Yeah, we're ahead of the other class, so we got plenty of time. At least right now we're ahead. Okay, so let me find my book. So it was 44? 44, okay. So we did something like this in class, but it's slightly different. And so let me just add this. So what it's asking for is it's asking how many ways can you group 15 people, a group of 15 people be divided into 5 groups of 3 people. So 15 people, 5 groups of 3 people. So before, what we did was, let's just review what we looked at before. We had 15 people, and we had groups of different size. You had groups of 5, 4, 3, 2, and 1. And in that case, what we did was we said, well, if we have 15 people and we take 5 of them into a group, there are this many number of groupings you can do with those, taking 5 people out of 15. And then we said, well, now we only have 10 people left to choose the next group. And so to do the group of size 4, so we did 10 people 4 at a time. And then once you pick that group of 4, there's only going to be 6 people left. So you have 6 people taken 3 at a time because you got a 3-person group. Yeah. Yeah, no, I'm going to get to that in a second. Okay, so hold on. I'm reviewing to show you why this one's different than what we did before. Okay, and then we had 3 people left over to take 2 at a time, and then we had one person one time. Okay, so we got a number. Now what's different about this one is that you do the same thing. You would go through and you would pick 3 people out of the 15 as the first group. So you'd have 15 people to choose from for the first 3-person group. So just repeating the same kind of procedure. We have a group of 3 out of 15. Then once we pick that group of 3, we have 12 people left, and we're then choosing 3 more people out of that remaining group of 12, and then we have, after you've taken 3 more people, after you have 9 people left, so you have 9 people to choose from for your next group of 3, and then you have 6 people left, and you pick a group of 3 from those, and finally you have 3 people left, and you just put them in the remaining group. So you may think, well, I'm done, but that's not what, you've got one extra step. And the reason you have the difference between what we did in this problem and what we have in this problem, does anybody know what is the difference? Well, in this one, all the groups have different sizes. So they're distinguishable from each other just because of their sizes. In the case of this, where you have 5 groups of 3 people, if you choose a group of 3 here, or you choose a group of 3 here, and it's the same group, it's not a distinguishable group. So what you would have to do, is you have to say, okay, now I've got these groups of 3 people. I have to basically take where those different groups of 3 people are located, or where I chose them, and take that out of the equation, because it doesn't just because they're in a group of 3 chosen here versus a group of 3 chosen there, it's still the same group. We're not saying that we're not distinguishing that it's the first group we chose or the second group we chose. It's just a group of 3 people. So you have to divide by 5 factorial, because I've got 5 groups of 3. So I've got 5 groups of 3, and there's 5 factorial ways of grouping those 5 elements. So that's why you end up dividing by 5 factorial, is to remove. So if you had, I think probably one of the other, say if you had 15 people and you had 3 groups of 3 and 1 group of 4 and 1 group of 2, so that's still 9 plus 4 plus 2 is going to be 15. So this is another way of grouping the people. You've got this group of 3 groups of 3. So the way this one would work, just to show you how it kind of the logic behind the whole thing, you would start out, and again, it doesn't matter which order you choose them in, so I'm going to do all the groups of 3 first. So you'd start out with 15 people. You choose 3 people from those 15 people. That would leave 12 remaining. You choose 3 out of that group of 12. You'd have 9 people remaining. You choose 3 out of that group of 9 that are remaining. Then I would do my group of, let's say, 4, so I'd have 6 people left. I would take 4 out of those, so that's how many different ways I can get subsets at this point, and then I'd have 2 people left, and I'd stick them in the group of 2. But then I'd have to divide by 3 factorial, because I have 3 groups of 3, and those 3 groups of 3 can be arranged in 3 factorial different ways. So to remove that effect of ordering, I have to do that. So does that make sense to you guys? why we have to do it. It's the number of times that you have repeats of, the other option I could have. Now you could have 4 groups of 3 and 3 groups of 1, and then you probably have to divide by 3 factorial and 2 factorial. So that's all. You won't have anything that complicated on the test, but that's why that happens. So I think there's another one. Let's see, is there another one that looks, the next one, how many ways, 45 says, in how many ways could 8 people be divided into 2 groups of 3 people and a group of 2 people? And so because you have 2 groups of 3 people, you divide by 2 factorial. So it kind of makes sense. Okay, back to the last section. So we'll finish this up fairly quickly. So we're doing more card stuff. So it's saying how many, if we have the 52 card deck and we pick okay, so what it's asking for is how many of those 52 cards, if I choose one randomly, how many of the 52 cards will have, in this case, at least one card is not a heart, okay? And so what they're doing is they're using the this is actually using the complement principle just with cards. So this is not really, it's not using the or thing, it's just using the complement. So if you're looking for the number of cards that have at least one card that is not a heart, the opposite of that is at least one card. Yeah, that's confusing me. At least one card. Oh, you're picking a 5-hand. Okay, let me read this again. I haven't looked at this for a while. Among the 2,598,960 possible 5-card poker hands from a standard 52-card deck, how many contain the following cards? At least one card that is not a heart. Okay. I've forgotten how to do this one. Let me just look at the book. Let me look at the problems here for just a second to remind me what I'm doing. Yeah, well, they actually help us out here because they're saying that this is the same as, well, the complement of this statement is, so they're saying this statement is a complement of all hearts. So what they're saying is to be able to solve this problem, you need to look at the total number of possibilities and subtract the complement of what they're asking. So what they're, the question is how many card hands out of that 2 million are all hearts? So the way you do that, so we'll say the number of card hands that are all hearts, which is the complement of what they're asking. To calculate that, what you do is you say, well, I've got 13 cards that are hearts, and I'm going to take 5 of those cards for a 5-card hand, and that's going to give me the number of hands that are all hearts. So let's calculate the number here. So we have 13 factorial divided by 5 factorial times 13 minus 5 quantity factorial, which is, let me move it over a little bit so I can have some space. So it's 13 times 12 times 11 times 10 times 9 times 8 factorial divided by 5 factorial and 8 factorial. So I've done the calculation in the parentheses. 13 minus 5 is 8. So I go all the way down to 8 factorial, cancel those out, and then I get my calculator out and do the multiplication. And I remember to divide by 5 factorial. So I've got to divide by 5 times 4 times 3 times 2 times 1. So let's do that. 13 times 12 times 11 times 10 times 9, and we divide by 5 and 4 and 3 and 2 and 1. And we come up with 1,287. So there are 1,237 hands out of that are all. Oh, there's Carol. Hi, Carol. So I'm in my class right now, so you can listen along if you'd like. But yeah. So we'll use the same. So Carol's the teacher that's teaching the class over in Perry McClure, so she probably was checking to make sure she could actually do it today. Anyway, that's kind of a surprise. So this is the number of 5-card hands that are all hearts. So to answer the question of how many 5-card hands out of the possible 2,598,960 we take that satisfy this requirement, we just subtract the complement where they're all hearts, and therefore the ones that are the opposite are going to have at least one heart, or not going to have at least one card that is not a heart. Okay, it's kind of that the whole sentence is really confusing sometimes. It's kind of like a double negative thing. Yeah, I know. I'm reading that, I'm going like, what? Okay, so if you subtract that, you get 2,597,673. So what they're saying is that pretty much all the time, except a very small percentage of the time, or if you get a hand of poker, you're going to have at least one card that's not a heart. There's very few that are all hearts. Okay, let's try this. At least one face card, the complement of no face cards. So again, what we're going to do is we're going to answer, instead of answering this one, we're going to answer the complement. So the question is, how many card hands have no face cards? Well, what we have is we have 52 cards, and how many cards are not face cards? 40. So that is not correct. Got to be careful here. So we got 40 cards to choose from that are not face cards. We're going to take 5 at a time. So that's what we're doing here, to find the number of hands that have no face cards. We take the number of cards that are not face cards. We take those 5 at a time, and that'll answer the complement question. So again, the combination formula says it's 40 factorial divided by 5 factorial times 40 minus 5 factorial, which is 40 factorial divided by 5 factorial times 35 factorial, which is 40 times 39 times 38 times 37 times 36 times 35 factorial divided by 5 factorial times 35 factorial. So the 35 factorials cancel out. So we end up with 40 times 39 times 38 times 37 times 36 over 5 times 4 times 3 times 2 times 1. And I'm going to stop there for just a second to remind you, every time we do a combination problem, what we're doing is the numerator, after we've simplified it like this, the numerator is using the fundamental counting principle to ask the question, how many arrangements do I have, where order is important, of, in this case, 5 cards. So what I would do, my process, it's a five-part process. I get the first card, dealt the first card. That there are 40 possibilities that are not face cards. So I get one of the face cards, one of the ones that are not face cards, and then I have 39 cards left. So then I get dealt one, I arbitrarily get another card or randomly get another card, but I can't have the same card that I started with, so I only have 39 choices for my next card. And likewise, when I get my third card, I've already used up 2 of the cards, and you have that 5 times because your 5-step process. And what that's saying in there, order is important. The fundamental accounting principle, for one thing, says that repeats are not allowed. So every time I deal a card, I don't have the same number of cards. I always have one less. And this has to do with arrangements. Then ultimately I divide by 5 factorial. And what this does is it says for a card hand that the order is not important as far as when you get the card. It's just that you get the card. So the denominator is we are removing the impact of order. And that's what we did with the one that Tanner just asked about. When we had 5 groups of 3 people, whether we pick the group of 3 people first or third, it doesn't matter. They're still the same group of 3 people, and that removed the effect of order on our calculations. If you don't have, if order is important, then you don't divide by that factorial. Okay, now this one's kind of complicated, but I'm going to try to explain it anyway. So it's problem 35 in the book. Let me make sure I say it exactly correctly. So it says a donut shop has a special on its mix and match selection, which allows customers to select 3 donuts from among the following varieties: plain maple, frosted chocolate, glazed, and jelly. How many different mix and match combinations are possible? And whenever they say mathematics teacher calendar problem, that means it's hard, because it's a problem that's supposed to be challenging math teachers. So this actually is not a combination problem. It's not you almost have to list. So what I'm going to do is I'm going to show you how to do it in a spreadsheet, and you just have to look at what they're asking and then come up with the answer. So let me see if I can find my spreadsheet here that explains this. Is that it? Let me check here. Oh, there we go. Yeah. So let me share this screen. So let's see. Start sharing. Spreadsheet. So what they're actually saying is that the first, you can see when I put this thing together, if I read the problem correctly again, it says, allows the customers to select 3 donuts from among the following varieties. How many mix, I'm trying to remember how this thing works again. Yeah, now I'm having a memory lapse here again about how this thing worked. Let's just look at it. Maybe I can figure out what it says here. So it looks like what I'm doing now that I look at it. So you have basically you have 2 that are matched, and then you can choose any of the remaining, including the original donut. So you can have 2 planes, and then the third one is any one of the 6 choices. And then the first 2 is can be maple, and the last one can be any one of the 6 choices. And if you continue that process out, just trying to look at it, and I think I actually had to look at the solution manual to figure out what the heck they were talking about. It wasn't very obvious. But that's what it ended up talking about. And ultimately, you had to answer the problem by creating a spreadsheet and then just counting them. Sometimes you just have to revert back to counting them. There's no fancy mathematical formula that tells you what the answer is. So that wasn't very satisfying. Not as satisfying as having a donut. So anyway, that was kind of the hardest problem. So there's the homeworks for section 5. Did I assign that already or not? I can't remember. So this is due next Thursday for the test. I think I already assigned it, but I think I might have shown it at the beginning of class. It's interesting teaching. Well, so I teach 3 classes. I teach calculus and teach physics with a physics lab, and then I teach this class. They're all very different. A lot of times, if you're a college at a larger school, if you're teaching math, you're probably going to teach. Well, one thing is, at a 4-year school, you teach typically 2 to 3 3-hour classes. So it'll be 9 credits. At a community college, you have to teach 15 credits. So you're already teaching 50% more. And at a small community college, you're teaching, in this case, 3 different classes. And then you have the 2 sections. I get lost figuring out where I have to change my mind from calculus to physics but it's not as bad as high school because they don't get enough time for their brain to rest to do anything. Okay, so we're going to move on to chapter 11 now. So we're going to use a lot of the stuff that we have learned in chapter 10, because probability is basically counting things, and it's comparing the number of what we would call favorable events to the total number of possible events. So it's, as you can see by the formula for probability, and this is theoretical probability. So P stands for probability, E stands for event. This is in your book, so it's one of those green things. So the probability of something, a favorable event occurring, what you do is you look at the ratio of the total possible events, unfavorable and favorable, which is the total number of outcomes. I'm going to put this on one screen so it's a little bit bigger so you can see the formula better. So you look at the ratio of the number of favorable events to the total number of outcomes to the total number of outcomes. In probability, it's a binomial type result. You either have something that's favorable or something that's unfavorable. And the favorable is what you're looking at. It doesn't have to do with whether you like it or you don't like it. So it's slightly different. So in this class, if I said if I put everybody's name in a hat and I pick a name or a name out of the hat in a random fashion, so I shake it up and I put my hand in there, close my eyes, and I pull it out. When I talk about the probability, I'm talking about what's the chances of me picking a name that's either a female or a male. And, it could be anybody. It could be either one, and it doesn't always end up being the theoretical, because it's either going to be a woman or a man. If you think about it, about half the time it's going to be a woman. It's actually going to be more likely to be a man in our case because we have more males in our class than females. But if I say, what's the probability of a woman being chosen, then picking a woman is a favorable outcome. If I ask, what is the probability of picking a man, then picking a man's a favorable outcome. So it has nothing to do with whether you like women or like men, or it has nothing to do with personal preference. It's whatever you're asking for the probability of. That's the favorable outcome. And something has to be either a favorable outcome or an unfavorable outcome. There's no, it's a sort of a favorable outcome. It's either one or the other. So what we'll end up with, this number will always be the number of events, the number of elements in the favorable event, or the event, is always greater than, or always less than or equal to the total number of events. So the probability is always a number that's between 0 and 1. It can be equal to 1, but it can't be greater than 1. So let's just look at an example of something that's pretty simple. So here's some examples of theoretical probability. So you roll 1 dice. What are the chances of getting a 3 compared with the other numbers? So the way you look at it is, okay, so what is the favorable outcome defined as here? So in our case, our favorable outcome is rolling a 3. Our unfavorable outcome is not rolling a 3. So when we look at the definition of the probability of, I'll just put 3 in there to show that's the probability of getting a 3, is the number of favorable outcomes. Well, I have 6 total outcomes because I have 6 sides to the dice, but only one of those 6 sides, which is the side that has a 3, is a favorable outcome. So the probability of rolling a dice and getting a 3 is 1/6, 1/6. You could also represent that as a percentage. So what you would do is you would take that ratio, 1 divided by 6, as a decimal. So 1 divided by 6 is, as a decimal, it's 0.166, repeat. So that's another way. So you can either say it as a fraction, or you can say it as a decimal between 0 and 1. Or you could rewrite this as a percentage, and to do that, you just multiply by 100. So it's 16.6%. So the probability of me rolling a dice and getting a 3, a fair dice, is 0.166. And it's the same with all the other numbers. It's 0.166 for each number. If I ask the question, but if I ask the question, what is the probability of rolling a 1 or 5, in this case, there are 2 favorable outcomes. So the probability of getting 1 or a 5 is going to be now 2 divided by 6. There are 2 favorable outcomes. There's still 6 possibilities. And you would simplify that down to 1/3, or 0.33, or 33.3%. So you can show it in those 3 forms. They're all equivalent to each other. This is in the rational number form. This is in the decimal form. This is in the percentage form. But they all mean the same. They're all the same thing. The unfavorable, in this case, would be rolling a 2, 3, 4, or 6. So theoretical probability is limited to events which are equally likely to happen. So things like coins, flipping a coin, the probability of getting a heads or a tails for one flip is 1/2, because there's two possible outcomes, two heads or tails. If you say, what's the probability of getting a head, a favorable outcome is getting a head. An unfavorable outcome is getting a tails. And so the ratio of the number of favorable outcomes, 1, to the number of possible outcomes, 2, is 1/2, and that's the probability. Rolling a dice, depending upon what they're asking about, there's the probability of, if you roll one dice, it's 1/6 probability of getting each number. One of the dice games, I guess, you add the numbers together, right? And so if you add, what's the probability of rolling 2 dice and getting 2 dice that add up to a 6? That's a little bit more complicated, but it's a random event, and it's equally likely to go on either side as far as the rolling. The same way with cards, dealing cards, as long as you shuffle them and you randomly pick, well, it doesn't really have to randomly pick, I guess, but picking a card is going to be equally likely to pick any one of the 52 cards. So you can do theoretical probability for situations like that. Now there's another kind of probability that we'll talk about, which is empirical probability, and that's through experiments. So it's like getting a disease, say cancer. So let's say it's liver cancer. So you might have, what's the probability of someone who's not a smoker to get liver cancer? There's no theoretical way of determining that. You have to look at a sample of people and find out, follow them and see how many total people you have and how many people have a favorable outcome, which in this case is getting cancer, but yay. So that shows you where favorable is not something that's always good. It's just the thing that you're asking, the question in that. Okay, so this is a simple example. It's one very similar to what I put on the test. So it's similar to what I just talked about in class. So it says there's a group of preschool children, including 9 girls and 7 boys. If Kim randomly selects one child to be first in line, with E being the event that the one selected is a girl, give each of the following. So in this case, they're defining the positive outcome as being a girl when you randomly select somebody's name or select a person. So they're kind of guiding you through the questions that you have to ask to come up with a measure of the probability. So I'll just do the answers over here. So A, what are the total number of possible outcomes? 16, yeah, because there are 16 children. The number of favorable outcomes, 9, because the girls are favorable in this case. Number C, the number of unfavorable outcomes, 7. So in this case, picking a boy is an unfavorable outcome relative to the question they're asking. The probability of event E. So the probability of event E is the ratio of the number of favorable outcomes to the total number of possible outcomes. So B is the number of favorable outcomes. A is the total possible outcomes. And so that's your answer, 9/16. Now they ask about odds. We haven't talked about odds, so we'll come back to that. Pardon me? Yeah, just a bit over half. Okay, this is a table that's in your book, so don't try to write it out. And we looked at this the other day, but this is a little different. So what they're doing is, if you had a 5-card hand of poker, and you have a deck of 52 cards, and you randomly pick 5 cards, deal 5 cards, to figure out the probability of getting each type of hand, you have to know how many favorable outcomes there are possible. And so there are 4 possible royal flushes, 1 for each suit. There are 36 straight flushes, 624 four-of-a-kinds, so forth and so on, through all these different kinds of card hands. 1 pair is 1,098. So if I ask the question, what if a 5-card hand of poker is dealt, what's the probability of starting out with having a full house, for example? What is the probability of being dealt a full house? Question mark. So again, the probability of getting a full house is equal to the number of events for the favorable events. In this case, the favorable event is getting a full house. So there are 3,744 possible full house hands, and the total number of 5-card hands is 2,598,960. So we just take the ratio of those two. So we could just leave it as that. I'm going to put it in a decimal form. So that comes out to be 0.00144, or 0.144%. You can think of this as a fraction. If you write this as a fraction in terms of 1,000, you'd have 144 out of 10,000. Okay, so this is if you take one. No, that's not right. Yeah, that's right. So if you take this one, so we're converting the decimal into a fraction. So what we do is we go 1, 2, 3, 4, 5. So what we want to do is get rid of all we want to move this far enough so we get a whole number. That's the whole idea here. So you go 1, 2, 3, 4, 5, which is 10,000. 10 to the 5th is 10,000. And you can plug that into your calculator and you can see it's true. So what that's saying is that if you were dealt 10,000 hands of poker, that 144 of those would be full houses. It doesn't happen very often. If you were dealt 1,000, you would get 14 hands. If you were dealt, is that right? If you're dealt 100 hands, you'd have, well, actually, it'd be it's going to be less than 1 every 1,000. I think I've got an extra 0 missing there. Let's just plug it in my calculators to see. You always can check that out. So let's make sure. Yeah, so it actually should be 144 per 100,000. So this is definitely true. 1, 2, so it's 0.144%. If it was 1%, then it would be 1 out of 100. So because this is 0.1%, it's approximately 1 per 1,000 hands that you would be dealt would be a full house. You'd have to play a lot of poker to be dealt a full house the first time. What's that? Let's look at. I'm going to make this up here. Let's look at rolling a dice and the chances of them adding up to 7. So what I'm going to do is I'm creating a table. This is back to chapter 10. So I'm creating a table, and these are the numbers, the possible numbers of the 2 dice. So one dice can have 1 through 6, the other dice can have 1 through 6. And if we add the two together, we generate, if we add these two numbers together, we'll get 2, 3, 4, 5, 6, 7, 3, 4, 5, 6, 7. 5 plus 2 is 7, 8, 4, 5, 6, 7. And then we just kind of keep incrementing them as we go along, try to concentrate. So I'll shut up and let you can. So, there are 36 possibilities. How do we know that? Fundamental accounting principle says you take the number of possibilities for the first step, which is rolling one dice, 6, times the number of possibilities for the second step, which is 6, so you get a total of 36. So this tells you exactly what the sum is, which you can't answer doing the fundamental accounting principle. Apparently, I've got something wrong here. Do I? No, I don't. Okay. Well, yeah. Okay. I was looking. Yeah, it's great. So now all we have to do to ask the probability of a certain occurrence is we just have to do an accounting of how many favorable occurrences there are. So if I ask the question, if you throw 2 die, is that the proper? Is that proper, right? There are 2 die. What is the probability that the sum will be 5? So, what is our favorable event? Yeah, to roll the dice and get a sum of 5. What's the unfavorable event? Yeah, anything other than a 5. And the total number of events is just the number of possible arrangements for the 2 die. So the probability, in this case, the probability of sum of 5 is the favorable one. So we just go over to our table and we count that 1, 2, 3, 4. So there's 4. So there are 4 favorable events. There are 36 possible events. You can simplify that down to 1/9. So the probability of throwing 2 die, the sum being a 5, is 1/9. It's 0.11111. I think if that's what 1/9 is. Or 11.1%. Any one of those. So if you end up with a calculation that just involves, unless I tell you specifically to do in percent, you can just leave it as a ratio of numbers. You do want to simplify it if you can simplify the fraction, but you don't need to put it in a decimal form.
Okay, your attendance question for today for this class is, I want you to go to Wikipedia, look under timeline of probability and statistics. You can just put that in your search window. And I want you to find out what happened in 1654.
Okay, so that was theoretical probability. That deals with a lot of things that it's gambling, I guess, flipping coins. So you can gamble over anything, I guess, but those are gambling things that are easily made fair, or picking things out of a hat, like picking lottery numbers. you can come up with an empirical probability there. The empirical probability is 1 out of whatever the total number of arrangements are. So it's, but there are other cases where we don't, it's not a mechanical process. It's not a completely random process. In some ways, this does have some random nature to it, but. So I always use free throw percentage as my example of empirical probability. And so the question is, how do you determine the empirical probability? Well, you have to do experiments of some kind. So somebody, if you were looking at a person, you said, what's their free throw percentage? Well, you have no idea, right? You said, well, does he play basketball? Well, that might help you a little bit. At least you can have hopefully he shoots better than 50%, but that doesn't, Shaquille O'Neal couldn't shoot better than 50%. So just because you're a basketball player doesn't mean you have super great free throw shooting talents. You could analyze you could look at their form without seeing them shoot a basket, just to see if they've got good form, because the better form you have, the more likely you are to be a good free throw shooter. But ultimately, it comes down to you've got to shoot some ball. You got to shoot balls, and whether you're doing it by yourself in the gym or whether you're doing it based on the performance in a game, you do an experiment and you come up with a empirical probability. So again, if you were a statistician for a basketball team and you get to the end of the season to figure out what the empirical probability, his free throw percentage is basically his empirical probability of making a free throw, because at that point he's taken a lot of them. So instead of the number of events, it's still the same rate. It's the ratio of favorable events to the total number of events, or in this case, experiments performed. If you were shooting a free throw, that would be the number of shots you've taken, and the number of events that what we're talking about is you either make or you miss a free throw. So again, it's a binomial situation. It's one or the other. The favorable outcome in this case would be making the free throw, and the unfavorable event would be missing the free throw. But it's through experiments. Now you could do an experiment like a coin. You could say, well, there's two sides. You could be weird about it and say, oh, there's two sides to this coin. I really don't know which. Is it more likely to land on one than the other? I don't really know. So you could do a theoretical empirical probability of flipping a coin. And if you only did 10 flips, you might get 4 heads and 6 tails. Or you might get 4 tails and 6, whatever. What are the opposite was that? Yes, go ahead. Are they fair coins? I think well, yeah. I mean, yeah. I don't know. Well, that's what you would do. You would do an experiment because you really can't tell. You assume that a coin. I guess if you made a coin specifically for flipping, you'd have the same thing on both sides of the head. You'd have symmetry. Whether the fact that one side of the coin is different than the other, I don't know whether that affects how often. It may or may not. But if you flip a coin 10 times, you might get 4 heads and 6 tails, and you can't at that point say, oh, the probability of flipping a coin is 40% one way and 60% the other way. So, the more times you flip a coin, the more likely the measured or the empirical probability will approach the theoretical probability. But even flipping 1,000 coins, the chances of getting 500 out of 1,000 is, we can actually answer that question. It's kind of interesting. If you flip a coin 1,000 times, what's the probability of getting exactly 500? We'll answer. Well, I'm not sure if that's a lot of coins to flip, but it's not super hard. So this is what I'm talking about here, what I'm trying to lead up to. The law of large numbers. as an experiment is repeated more and more times, the proportion of outcomes favorable to any particular event will tend to come closer and closer to the theoretical probability of that event. So even though you may not get exactly 500 out of 1,000, if you flip if you flip a coin 10 times, the average that you come out to is not going to be as close to the empirical 50% as if you do 100 coins or if you do 1,000 coins. So the more experiments you run, the more likely the outcome, the more likely that the empirical probability is going to be closer to the theoretical probability. So that's why you run lots of experiments. If you're trying to determine something empirically, the more experiments you run, the more accurate your results are. But the more experiments you run, the more time it takes, the more money it costs. So there's a trade-off. And the question, which we won't answer in this class, but if you take a more advanced statistics class, is the question of how many experiments do I need to run to get an accurate result? How many people do I have to try this cancer treatment with to know that it's effective? I want to have a good probability of knowing that it is effective, because you don't want people to go through the side effects and the cost of chemo if it's not really going to help you or not. Or eggs, how many people like eggs? Okay. Are eggs bad for you? Who knows? That's the question. So if you like eggs, you like to eat eggs a lot, are you willing to risk the health? If there is there actually a health problem with eating eggs? You'd like to know that. At least you can make some kind of decision, and you want to be certain one way or the other. When I was in college, the guy that was the best man at my wedding, he was a poor college student, and so he did a study for the Egg Council. This was back in 1970, 78 maybe, and the whole thing about cholesterol and how eggs would affect you. And so he did this experiment. They had a bunch of people at Virginia Tech who did and then they took blood samples and checked to see whether but it was good for him because it was free food. So I think he got paid, and then he got to eat a lot of eggs, which was, and I think what I remember was that you got a kind of like an initial spike when you started eating a lot of eggs, but then your body kind of adjusted to it. It wasn't really as bad as people made it out to be. And what you're finding out nowadays is that those kinds of things that were supposedly bad for you are not that bad for you anymore. Here's another example. So my family, and I don't know if this has anything to do with where we came from, but when I was growing up, we never had margarine. We always had butter. So, and I never heard anybody talk about the detrimental effects of eating butter in my family. So then I got married to Martha, and her family had always had margarine. And then there was the supposed, back then, margarine was supposed to be better for you than butter. So then I'm starting to eat margarine all the time, because I don't, one thing as a husband is you don't want to say, well, that's what my mom used to do. You just don't bring that up. You just go along with your wife. So we had margarine for so many years. Now that they found out that butter isn't as bad for you, and that margarine, depending upon how the margarine's made, can be really bad for you. So I'm hoping that my years from 0 to 20 were such that I built up the damage my wife did to me by forcing me to eat margarine. It's just the way it's like trans fats. It's a certain fat that it's a manufactured fat, and so nowadays we eat butter all the time. It's butter, and I like butter anyway. So, but I was. Can we have butter? Because that's what my mom used to do. But we should have listened to my moms. Okay, so this is the same kind of thing. A series of repeated experiments provides an empirical probability for an event, which by inductive reasoning is an estimate of the event's theoretical probability. Increasing the number of repetitions increases the reliability to the estimate. Likewise, an established theoretical probability for an event enables us by deductive reasoning to predict the proportion of times the event will occur in a series of repeated experiments. The prediction should be more accurate for the larger number of repetitions. So this is just using the law of large numbers to say that the more experiments, the more information you have, the more facts you have, that you should be able to then use inductive reasoning to come up with some conclusion. Things like global warming or whatever this, or whether it's cancer caused by asbestos. You do experiments, you do analyze data to then say it's bad for you, or the planet's warming and you ought to do something about it. Okay, so let's just do a few more problems like you're going to have for homework. So we're going to do the possibilities of tossing coins. 3 fair coins are tossed. Write out the sample space. Determine the probability of each event. So one way of writing out the sample space here would be to write all the possibilities of heads, tails, and stuff. But we've just recently come up with a way of figuring out what the sample space is. So I'm going to do it the way that's a little more compact as far as the calculation. So remember what we said was we've got 3, so we're tossing a coin 3 times. So we can answer the question of no, what are they asking for? Heads. Okay, no heads, 1 head, 2 heads, and 3 heads. And we showed that you can use combinations to calculate those numbers. So it's always the number of tosses is the first number, and the number of occurrences is the second number. So each one of these is going to be a combination of 3 things taken 1, 0, 1, 2, and 3 at a time. And we could calculate those, or we could look them on Pascal's triangle. I'm just going to tell you what they are. They're 1, 3, 3, 1. So those are the number of arrangements, or not the number of arrangements, but the number of arrangements that have 1 head, 2 heads, 3 heads, 0 heads. And if you add those together, you get 8. And that number 8 can be determined by taking this 3-part process, flipping the first coin, flipping the second coin, flipping the third coin, each with 2 possibilities. And you could just get number 8 by taking 2 raised to the 3rd power. So you can do it 2 ways. The third way is listing all the possibilities. The way we're going to use is this compact form to find out the number of occurrences, and if you, of each situation, and you add them together and gives you the total number, which we can confirm another way by using the fundamental counting principle. So to answer the probability of each one of these events, it's pretty easy. So that's part A. Part B, probability of no heads. It's the number of occurrences of no heads divided by the total number of possible occurrences. For 1 head, exactly 1 head, it's going to be 3, because there are 3 cases where you can have 1 head, divided by the total number of possibilities. Probability of getting 2 heads. Favorable outcome is getting 2 heads. There are 3 of those out of 8. And finally, the probability of getting 3 heads. There's only 1 arrangement that has 3 heads out of 8 possibilities. And if you add all the probabilities up, you should get 1. Because the probability of well, let me go back again. These are the probabilities for getting each of the combinations. It has to be one of these. So the probability of getting no heads or 1 head or 2 heads or 3 heads using the OR, you can see we just add all the stuff together. Because the sum is just saying what's the probability of flipping 3 coins, really. Well, that's up to you. If you flip 3 coins, it's been done. So if you did 4 coins, how would you do that? Well, you would have 2 to the 4th, which is 8. So you'd have 8 different arrangements. You could have 1 head, 0 heads, no heads, 1 head, 2 heads, 3 heads, 4 heads. I guess that would be it, right? So you'd have 16 possibilities. So let's just do that while we're at it. I usually put something like this on the test, so I'm going to help you try to beat this into your brain. So let's say we had 4 flips. So in that case, you could have no heads, 1 head, 2 heads, 3 heads, and 4 heads. So those are our 4 possibilities. So to find the number, you'd take 4 things 0 at a time, 4 things 1 at a time, 4 things 2 at a time, 4 things 3 at a time, 4 things 4 at a time. Anything taken 0 at a time is 1. Anything taken the same number as this number being the same as 1. When you take something 1 at a time, it's always 4. And since this is symmetric, we know this is also 4. So the only one we'd have to calculate. So we get these just because we know these extreme ones, 4 at 0 at a time and 4 at 1 at a time, they're 1. The next ones in are always this one. 4 things taken 1 at a time, you pick A, B, C, or D 1 at a time, so there's 4 choices. Because of symmetry, this is 4, and the only one we have to figure out. That one, if you look at Pascal's triangle, that's 6. Notice if I add all these together, I'll get 16, which is what I expect. And then the probability of flipping a coin, 4 coins getting 2 heads is going to be 16 divided by 6. Everything's going to be divided by 16. Okay. I'm going to skip that one for a second. This will be the last thing we talk about. So we haven't talked about odds. Odds are very closely related to probability. Again, this is in your book, and you just need to know how to calculate them. So if all outcomes in a sample space are equally likely, okay, like flipping a coin, rolling a dice, picking cards, A of them are favorable to the event. That's the numerator in probability. The remaining B outcomes are unfavorable. That's not in the definition of probability, but it's related to it. Then the odds in favor of event E are A to B, and the odds against are B to A. Okay, so let's think about this. Let's go back to the problem that we didn't finish and calculate the odds and show you how it works. So if we go back to this, oh, maybe I skipped it. No. There we go. So here it says odds in favor of event E. So odds are favorable to unfavorable. So we can use the information given here. So the number of favorable outcomes is 7. and the number of unfavorable outcomes, sorry, the number of favorable outcomes is 9, which is B. The number of unfavorable outcomes is 7. So the odds, the probability is 9/16. The odds are 9 to 7. Notice that 9 plus 7 equals 16. So if you have probability, you can easily get odds by using the numerator as the first term in the odds and the denominator minus the numerator as the second term in the odds. Also, if you want to go from odds to probability, you add these two numbers together. That gives you the denominator, and the first term is the numerator. I'll formally should talk about that next time, but that's it for today. So we'll see you on Tuesday.